Without further ado, here's John's.
All right, thanks. Let's see if I can get this thing to refresh. There we go. This is the upper of this slide right here. It types for me. Hey everyone, my name is John Ziola. One quick housekeeping item. Is anyone here not comfortable being photographed? Good? Okay.
Thank you.
Because Alex would like to take pictures to help market this great location, so I appreciate that. Change your mind, just let him know, and then we can remove you. We can put a face over your face, something like that. So, all right. So, welcome to my talk. This is being recorded down on this little laptop and over there. Yins shouldn't be in it. That's a technical term. It means you all. You guys can be in it, but if you want to be in it, come up and say hi. All right. So, I have a bunch of different types of content that we could go through, right? The idea for this talk started a couple of months ago when there were some questions at another ISSA event. We were asking questions about containers and container security and things like that. And so this is going to be a little bit of an introduction, but if you find that it's going too slow for you and you want to speed things up, I've got some more advanced materials that we could also go through, and I'll try not to just keep talking through all of those for numerous hours on end. So I'm going to cover an introduction to containers, a little bit about container security. We're going to have some demos, and hopefully they work. A little bit about myself. I'm a Pittsburgh local. You may know me. You may not. I work at a couple of different companies. Hey, John. I have a SaaS company that I started a year ago called Zenable. We work on helping enterprises and tech companies adopt policies, code, and ways of doing GRC. I also co-own a consulting company with this guy right there, ISSA. So we help mid-sized companies with maintaining their GRC programs and getting advice on security and things like that. I also teach exams. So I teach the soon-to-be renamed Cloud Native Security and DevSecOps class. It's second priority if you want to look it up. We talk about AWS and Azure and go through how to secure applications in pipelines and deploy things into Kubernetes clusters and run safe Kubernetes clusters, right? That's essentially the 2-second pitch there. I'm also a CNCF ambassador. That means that I have lots of clothes like these because the CNCF gives it to me for free. It's also very warm and very cozy, and that doesn't come through very well. But yeah, so essentially what that means is, so if you're not familiar, the CNCF is an organization that was created to hold Kubernetes. But since then, it has a lot more projects in it, over 100 projects now. And as an ambassador, my role is just to help people find the right answers to their questions. So if you're adopting Kubernetes or something in the ecosystem or doing something cloud native and you have questions, my job, volunteer job, but my job, my hat, is just helping you with the right people, maybe help answer your questions directly or just get you in front of people who know the answers. In a lot of cases, that means helping you with the maintainer of the project you have questions about, because maybe they need to improve their documentation or something like that. It's kind of the angle that we take. So I do that. Also, I go to a lot of the events. So if you go to KubeCon or things like that, I am typically there. I'm definitely always at B-Sides. So who here has been to a B-Sides Pittsburgh before? All right, awesome. So like 2/3 of the room. The other third of you, come on out. It's July 11th. July 11th. Great. So it's the biggest conference in Pittsburgh. It's a really good time. We've got a couple of surprises for you all this year. There's usually a CTF, a lot of village, like 2 different tracks, maybe 3. I don't even know that we've decided. Did we decide? Okay, there's going to be 3.
The whole top of the casino.
Yeah, so we got like a whole bunch of room, and it's going to be fun. There's some surprises. I really want to tell you about them, but I won't. You got to show up and figure it out. I also run some groups like City InfoSec that you joined to come to this. I'm technically run that, but yeah, this is an ISSA event. So, everyone know about the giveaway?
Yeah.
1, 2, 3, 4. Okay, yes. Yeah, right, exactly. Of course you do. All right, so I posted something. I was just wondering how many people actually showed up and knew anything about it. I'm also an AWS community builder, and that means that they give me free money, and I can give you free money for AWS. So I've got $20, I don't know, coupon code things. So if you ask good questions, if you stop me on a question, or if I really like your question, I'll give you a $20 AWS thingy. Cool. This is also a reminder not to forget about it, so I'll put another slide later to remind us that this exists. I am going to give away a handful of those today. I've got a bunch, so. And when I was thinking about what I wanted to talk about, like I said, we started with the ISSA meeting, but I was like, well, I should do a poll too. And so this is the poll. What do you want most out of the ISSA container security presentation? The people voted and they said cloud native security, so we have a section on cloud native security tonight. We can audible and skip it or go fast, or whatever you'd like. I don't know what be something people wanted. They never told me. So if that was you and you want to tell me now, okay. So why use containers? Does anyone here who uses containers today, like at their company? Say half. Is anyone like super confident, like feel pretty comfortable with them? All right, I see just 1, 2, 3. Okay, 3. Cool. People are super confident. Like, do you have like a specific question, I guess?
They wanted to stump you.
They want to start me. Well, that's on the table. Was there any
Security is something else.
Okay, using them is one thing, securing them is something else. Yep, sure.
I'm just looking for methods to secure them. I'm familiar with JFrog and X-ray, things like that.
Yeah. Yeah. Awesome. How about you? Did you have anything specific?
To attend the talk.
Just hanging out? Cool. Me too. What about you? Yeah.
Because when I deployed my app code to Kubernetes, the security team came in and applied about 10 times more containers on top of that. And I'd like to know why.
Oh, interesting. So the security team deployed more containers in your cluster, and you're like, why?
Yeah.
Okay, cool. Are they like all daemon sets? Or are they?
So,
Okay, yeah. They're probably just a bunch of agents that trying to shove on all your worker nodes. All right, cool. So there's a number of reasons why you would want to use containers. Some of these might be obvious to you. You might want to horizontally scale, right? We're breaking things down into small bite-sized pieces. We can distribute them across systems. Horizontal scaling, probably. We want to be able to run one workload on one server or across 10 different servers. And we are able to implement services, right? And that means that these are kind of loosely coupled or decoupled processes, and they can scale independently. The cool thing about that is if you've got a traditional, what they call a monolith, it's like one big process, you say, and it gets overloaded, you have to add another server or two. But maybe just one little bottleneck, one little part of your application that's actually the issue that needs to scale up. And when you decompose it down into the microservices, you can get just that one thing that's actually the bottleneck, and not get all of the other things which aren't the bottleneck. Did you have a question? No? Okay. Also super portable. So, if you've ever seen the works on local, right? It works on my laptop. Like, okay, are we going to ship your laptop to production? Probably not, right? So we want to be able to reproducibly run a workload on a laptop, in a dev environment, in a prod environment, and for the most part, it's portable. These things are configurations. You can still configure their runtime, and Kubernetes uses the CRI, right? Runtime interface. But typically, you somehow impose configuration on the running of the container, but that aside, containers are extremely portable and they're immutable. They don't get changed, right? We actually have hashes, a number of different hashes that say that this has not been changed. That also means that you can deploy new versions of things and roll back very easily. Anyone here ever tried to uninstall a Windows patch and it went 100% smoothly? Right? Yeah, right, exactly. Yeah, it doesn't come off as well as it goes on. Right? The thing about containers is they do, right? You can just point to a different hash, and you will run that different hash, different pointer tag of a container, and you know that it's exactly the same as before. You might run into different problems. Your database, your data, your schemas, those are still problems, but the application code is immutable. You can constrain these things, right? They're called containers. They are contained. So you can set resource limits. You can max can set limits on the amount of IO that it can use, the amount of memory it can have, CPUs, the kind of fractional CPUs. They're more efficient than virtual machines. I'm going to put this down because I'm going to draw something on my screen in a minute. But there's less overhead than virtual machines. We're going to talk about that in more detail. It's kind of the way of doing things, it's the modern way of doing things. And so if you use them as your building block way of distributing information, it kind of fits better into modern technology like cloud providers, Kubernetes clusters, and things like that. And that's what I said. It enables these more modern tool sets and consistency. We kind of covered that already. All right, so that's why I use them. But what are they? A container is just a process. It's a process which happens to have been constrained in a number of different ways, right? You can constrain it using all kinds of different technologies, but it's just a process that runs the system in a constrained way. Now, sometimes in certain scenarios, on my back here, when I run a container, I'm actually running a container inside of a VM, and things get a little tricky. But if I'm on a native system, a Linux-based system, it is literally a process. I'm going to show you how you can make your own with Linux command line tools in the future. You have ways to limit, like I said, the memory, the disk I/O, the file system. You can use hitroot or chroot. You can limit the ability to hit API calls in the Linux kernel with second output files, SUX, AppArmor, all kinds of different stuff. And so this is my favorite side-by-side comparison of a container versus a VM. This is from Docker. So on the left here, we have containers, and on the right, we have virtual machines. And you should be generally, I'm assuming you're generally familiar with this idea. We've got servers down here. We don't really care about that part. On the containerization side, we've got an application, and that application interfaces directly with that operating system. This application runs on the same server, also hits that exact same operating system. So this is a weak security control, right? If you look at virtual machines, one app has one operating system, this other app has a different operating system. If there's a kernel level vulnerability, you are still going to have to break through the hypervisor to get to something else, which is much less likely, right? On the containerization front, if you get what they call a container escape, right? If you're able to live down here, you've owned all of these, right? So generally, as a security person, take this with a grain of salt, but generally you should not consider a container a security boundary, right? They are constrained, they are limited, but they're not a strict security boundary typically, right? Especially for high security environments. There's reasons why we have ways to envelop and encase these containers essentially in micro VMs, right? And that's for high security environments. So there are some environments where they actually wrap this thing in a very small operating system, and it's extremely specialized. You actually compile an operating system specific to what API calls, ABI calls, that the application needs to make to the kernel, and only those are in that kernel. So it's super small, and that's super cool. Most people don't use that kind of stuff, right? It's called a microkernel. So let's go a little bit deeper with containers. So if I wanted to make a container, I could do something kind of like this, and we're going to step through this in the terminal. But I could make a directory and put some stuff in it, files, right? A bin directory, a USR directory, an etc directory, whatever. And then I can run this command, right? Sudo unshare. We're going to make some new namespaces. We're going to configure a chroot jail to be this directory, right? Chroot, alpine. And then relative to this directory, we're going to run bin ash. That's like bash shell or the born again shell or born shell. And then below this line, you're kind of in a container, right? You've constrained yourself. All you did was make Linux API calls to constrain the process that you made right here, right? So that's a container. Does anyone know what this is? It's a container. If you run PS on a system that's running a container, it looks like that. It's just a process, right? That's a container. Woohoo. Very exciting. a lot of times when I ask people, like if you run a container and then you run PS and you list the processes, what would it look like? What would the parent of it be? What, kind of how would it look in your PS? And they say, oh, there's Docker, and then Docker like forks or has a child of this other process. And I mean, there are situations where that could be the case, but typically a container would be defined as something like this. It's just a process. All right. So any questions so far? Anyone think we're going way too slow, which is not going to hurt my feelings? Okay.
So how secure are containers?
How secure are containers? Containers are managed, run by a CRI, which is an abstraction layer typically. There's actually 2 layers of specification, containerd and then runc, which are the libraries that go from an idea of a container to an actual running process that's been constrained. And those things are pretty well tested. I think in 2022, there were container escapes like 6 out of 12 months that year for different specific runtimes. Sometimes specific configurations of those containers were only applied. But they should not be considered security boundaries. I don't know where that slide went. I think it's up here. Yeah, they should generally not be considered security boundaries. But if you want to make a micro VM and stuff a container in it, that's one way to mitigate that solution, that problem. Some people will make lots of small worker nodes in a cluster and segment it that way, so there's only 3 apps next to each other, or they'll do like taints and tolerations to have affinity, so that you put certain security levels of applications of containers next to other similar level of security containers, and so you can segment a little bit that way. But generally, you should expect that it's possible that someone would go from app F to app E somehow. That said, they're not that bad. They're not that bad. So it's like it's a risk assessment, right? Like what's the impact? What's the likelihood that this is going to happen? I think the impact or the likelihood should always be not 0. It could happen. It could always happen. It's also much more likely than like a hypervisor, escape.
You still have escapes from virtual machines as well.
Right. Yeah. It doesn't not happen. It happens a lot less frequently. It doesn't happen 6 times in a year, right? It happens once every few years.
Is the security stance for containers at a different level, like the benefit though, right? So you're talking mostly about escapes and stuff like that, but what about vulnerabilities in applications or software services that are running on the operating system, right? That is within where the app actually lives, right? So in a virtual machine, you've got an entire operating system which comes with all of the different pieces that you need to run that operating system. Whereas in a container, you only have the kernel level things that you need, as well as only the application level stuff that you need to run the app. Whereas on a VM, you're going to have a whole bunch of other things inside there. And so from that level of security, isn't it a little bit more secure in the container world because there's less
Attack surface.
Yes.
Yeah. Yeah. So you're essentially talking about attack surface reduction, right? So we mentioned root jails or pivot roots. And so what we're saying is, I think of DLLs a lot whenever I think about this, DLL hell. You could dynamically load lots of libraries which are on a file system. And if you're on an operating system, you have these directories open to you. Now, people could say, oh, we've got extended ACLs and file ACLs, and you could do very interesting things with that and get the same type of property, which is being unable to read these dynamic libraries and, pop a socket and reverse shell back home. Sure, it's going to be a lot easier to do that sort of stuff in a container. It's kind of what it's built for. It's a usability layer on all of those other primitives. It's not unique. It is using those things. And it's just kind of this usability, simplicity layer on top. So yeah, I mean, there are definitely benefits to it, which you could implement on operating systems, but it's more usable to do it in a container. Yeah. Yeah, Ron.
So how's the container communicate with another container or with or with the application? I mean, is there, will the container have a network stack, or?
Yeah, so if a container wants to make a network call, it calls the host operating system. And it sets up a socket, it does a handshake. All that stuff gets delegated as a system call from app F to the operating system, and then that network connection is made. If that network connection's destination happens to be app E, it'll just do it like that, right? It'll still route through the operating system, through the kernel, to get to app E. Typically, there are workarounds to this. If you have access to a file system, you might be able to send information between app F and E without touching, like sockets in the host operating system. And there's lots of other things, like if you're familiar with Kubernetes and you deploy 2 containers in the same pod, they talk to each other on loopback. That's by design how they're supposed to talk to each other. But if you talk to 2 different pods, you have to be a routable IP address. It might be private, but it has to be a routable IP address. And so that would go through the host operating system. Technically, in that case, it goes through the CNI, which is just a special way of saying code that is networking focused that runs around the operating system layer. But yeah, there's all kinds of interesting ways you can communicate with each other, not just over a network. Lots of people that, you might have a shared temporary file system and you drop a file there and another one reads it. And, if you have a very bad compromise of your system, you could have people passing information from high security, but the thing we broke into, low security, and is allowed to talk to the internet. Then we transfer the information over to this one and then pop out of the network to exfil. Things you can definitely see. Good questions. I think I finished all of these, yeah. All right, so we're going to just talk briefly about where containers run. So this is based off of a white paper. I'm a member of TAG Security. It's the Technical Advisory Group for Security in the CNCF. And we have a white paper called the Cloud Native Security White Paper. And I really love this set of 3 pictures and this terminology, this model, for talking about the phases of getting an application from an idea to production, right? It's standard SDLC stuff, right? We've got software development, and at the development layer, we'll think about things like the developer's IDE, where they're actually writing the code. And we'll have Docker files. That's where a container would come in, right? If you're not familiar, a Docker file is kind of like a bash script. I one time wrote some code to translate Docker files into bash scripts and bash scripts into Docker files. And I can tell you it works, and I can tell you you should never do this. This is a bad idea, but it does work. And I had a niche scenario where I thought it was a good idea. It wasn't, but it works. So you can think of it like a shell script. It runs commands, it sets environment variables, it downloads some files and uses them to make what they call a union file system. So a Docker file, or sometimes also a container file, is just this manifest, this list of instructions to make a container. Technically, it's not a container, it's an image. So there's a lot of overlap, I would say, and misuse of these terms. Technically, what we're talking about, there's 2 separate things. There's a container, and again, a container is a contained process, right? That means it's running. Like when I say container, I mean the process is running, the file system's on a disk somewhere, maybe it's in a RAMFS, whatever, it's somewhere. Then there's an image. An image is the code bundled up nicely with a bow on it, right? And you can store it in different places. It has metadata and manifest files and things like that. So technically, when I have a Docker file, when I build the Docker container, I'm actually building a Docker image. I make that image, I store it in a registry somewhere, and then when I want to run it, I download it, and now I've got everything I need to run this code. I've got all the instructions, all the code, all the everything's in the bundle. So, when we're developing code, we make the actual code. We make infrastructure as code to deploy our servers and whatever. We build an image, and we want to get that image moved on through the lifecycle to the distribute step. We need to distribute this thing that we've built in our CI/CD pipelines to somewhere, a registry, likely, right? And we can add all kinds of security checks in here. We can scan the Docker file itself, right, using a tool like a Hadalint or conftest. You can assess the literal text in the Docker file to say, is this okay? That's one thing you might do, and you don't need to build it in order to do that. I'm just reading the text. So I can do that on a developer's laptop. It's very fast. I can do it wherever I want. Some people would implement it as a pre-commit hook. So pre-commit hook is if you do software development, you're familiar with Git, G-I-T. And Git, you have this idea of staging changes, committing changes, and then pushing those commits around. You can add hooks into those Git commands. And so when you run git commit, foo, whatever, before it actually does the commit, right before, it can run a tool. It can run a script. And so that script can check your Docker file to make sure that you're not running as root by default or something that you want to enforce, right? That's something that you can do in pre-commit on your developer's laptop before it hits a server, before it's been built. You don't need to know how to build it. It might require some information be gathered and passed in as arguments. You don't need to know any of that stuff to check a Docker file. Then you get to the distribute step, right? This is where we're actually going to build it. We do need to know the arguments. We're going to pass stuff into it, and we're going to make the image, container image, which is a little confusing. We're going to make the image. It's an OCI image. That image, again, it's literally a tarball. It's a zip file, right? I will show you. I'm going to rip one apart and show you how it works in a little bit. But it's a zip file, and now that it's built, you use a different set of tools to evaluate it. So you use one set of tools to look at the text on a Docker file, a different set of tools to actually rip apart the contents of this tarball and look at the files that are in it. And it doesn't have to think about what's going to happen when I hit that curl off the internet and download the file. In the Docker file, I don't know what the result of that is. I'm just going to download something from the internet. So I can guess that it's bad or maybe it's fine. When I'm looking at the Docker image, I know what it was. I know what it pulled down. I have the file in front of me. So I can tell you if it's malware or not, or at least I can guess, right? And you could do all kinds of different application testing. This is where you'll commonly make software bill of materials, which is a common buzzy word lately. You store things in a registry. Maybe the registry will do the SBOMs for you or vulnerability scanning. An SBOM is just a list of what's in it, right? We're just trying to figure out what's in the darn thing. And then once we know what's in the darn thing, and hopefully the versions of it, we can map that against a list of known problems and come out with a list of vulnerabilities. Oops. And then we've got the runtime. So we can look at the text file, we can look at the built image, but sometimes that's still not enough because even though you have an image, remember earlier I said you still pass configurations to it when it runs. So if I deploy it in my runtime, it can have a default of running as a non-root user, but I can force it to run as a privileged root user at runtime. So I still need to look at things out in the actual runtime. So I might want to add a validating emission policy or something like that to a Kubernetes cluster to say, every time my cluster is being changed, someone wants to run something in my cluster, check for these things. And so it's kind of like that last ditch effort. Like right before you come into the cluster, we're going to check to make sure that this is okay, it's allowed. There's all kinds of other things that you could do here with like network access, that's the CNI that we've got there. Data access, that's the CSI. Everything is an interface. Everything is code in a Kubernetes cluster. So lots of C something I's. CRI is the runtime. And you've got all this other stuff too, right? Security and compliance, daemon sets running agents that might be helping or might be hurting. You don't know. Secrets management is a really good one, right? Like obviously you don't want to hard code your secrets. You want to retrieve them from somewhere. These are environmental things, and so you can put that can be the control. The fact that you have a vulnerability or an intel feed saying that this IP is bad, and so network access from that IP to this is something worth looking into. There's a whole bunch of different things that you want to consider. Hey guys. All right, so let's just briefly talk about, good call, the cookies, good call. Let's talk about CIA. So who knows what CIA is? Confidentiality, integrity, availability. If you've got any security certification, it's probably been like pounded into your head. Does anyone know what DIE is? Die. Yes. Good job. So CIA is a traditional way of thinking about cybersecurity, and regardless of everything I'm about to say, it's still valid. However, it's sometimes nice to think about things a little bit differently and to think about the way that your code runs and the architecture and design of it and see if you can get, as a side effect of a good design, some security properties. That's the idea of the DIE model. Workloads that are distributed, that are immutable, and that are ephemeral. Right? We're saying that if you happen to have a good design and you run your thing in a distributed way, in an immutable way, meaning it can't be changed, and an ephemeral way, meaning that when you need it, you've got it, and when you don't, you don't, you're doing the attack surface reduction, right? You're being, here, actually, I'm going to, all right, I've got that slide later. So let's describe these in a little bit more detail. DIE. I cherry-picked a couple pictures off the internet. They're all annotated at the bottom where I got them from. I did not make any of these. But distributed, like the de facto, is Kubernetes, right? So distributed systems, you've got lots of servers or worker nodes, and they run images, containers on them. They just run processes. Again, it's just a zip file that tells you how to run a process, and then it runs the process. It runs it on all of these different servers. And when the server hits some limit, like there's not enough CPU left or not enough memory left or our GPU's taking too long to do whatever, network latency is going up. Based on some metric, you can make more servers, right? We're going to use the cloud native, right? We're going to make more servers, and we're going to reallocate, rebalance things, if we can, out to those, and we'll just keep going. We'll keep getting bigger and bigger and bigger. Like some of the bigger clusters out there that I know of are around the 5,000 to 10,000 node mark, based on what Airbnb says at KubeCon all the time. But you can theoretically have a 10,000 server cluster, one cluster, 10,000 nodes. Some people say that's a bad idea. You should have lots of smaller clusters, blast radius, blah, blah, blah. The point is that you can distribute your workload because you've got these containers, little Lego blocks, building blocks that I can just snap off from this server and pop it over on that server. And I mentioned earlier taints and tolerations and affinities. You can generally, lovingly guide them to the right server for them. If you need a GPU, you should not go to the server with no GPUs, right? If you need lots of memory, don't go to the one with lots of CPU and no RAM, right? You can kind of fit the Tetris, fit it together the right way. But it's distributed, and it reacts, right? This is not like a car engine. I think of it more like an amoeba, like it gets stimulated by activity, and it responds to that activity. So it's Black Friday and you get lots of people going to your website, it will make more servers. When that activity dies down, it kills the servers and it condenses them and it tries to cost save a little bit, right? Immutability means that it doesn't actually change. So let's go back to this like Windows update example, or any update really. So if you have a mutable set of infrastructure, it means you mutate it, you change it. So if you have application v1 and on operating system v1, great. We need to release v1.1. You put it on that system and you reboot it. You point things to the new thing. You change it. You mutate the system. With a mutable infrastructure, instead, you have the old version 1. That's a typo. You have the old version 1, and you deploy the new version 1.1. You point things to the new version, and then you destroy the old thing. So I don't make a change to a server and run new things on it necessarily. Think of it more as, conceptually, deploying something in parallel, cutting everything over to it, and then destroying the old thing. Right? This means that rollbacks are very easy. Here, I need to unmutate. It can be sticky. Here, I need to redeploy that thing that's literally the same exact hash and point a load balancer or something, or an ingress controller. So distributed, right? Building blocks that can spread out and contract as you need. Immutable, doesn't change. You make new ones and kill the old ones. And then ephemeral. When you need it, it makes it. When you're done, it dies, right? So this is from Google. I love their blog on this. We have a container. It starts up when you need it to, right? When there's someone making a request. You serve those requests for a while, and then maybe you go idle because there's 1,000 instances of this container, but you really only need 100. So all of them are generally low CPU usage or low memory or whatever your metric that you care about is. They go idle, and then they'll shut down. right? And they'll kind of recondense things. And you can set a metric. You can make it so that your servers are regularly running at 80 or 90% CPU, and that's exactly what you want. And it will only make new servers whenever you hit the 98th percentile or something along those lines. So if you compare and contrast these two ideas, if you have a distributed system, it's by definition resilient, so you get availability, right? If you have ephemeral workloads, conceptually it's fast moving. So it's hard to breach confidentiality. This is the softest justification. But it's a little bit harder, right? Like, I'm going to compromise with remote code exec this serverless function and drop something on it and get a reverse shell back. But by the time the reverse shell hits, the thing gets killed. Like, crap, I didn't get to finish the exploit because I literally had 7 seconds. And I can't figure out a way to do the exploit in 7 seconds. That's what we're talking about here. We're not saying that just because it comes up and comes down that you can't steal the data. You can still steal the data. And then immutability is integrity. Like, that's literally the definition. Like, integrity, immutability is the same thing, right? So immutable environments cannot be changed. That gives you strong integrity. That gives you CIA. So CIA is still important, but if you focus on a quality modern system first and design it with DIE, you get CIA as a side effect, but your developers hate you less. And that's what I love about it, right? It's a beautiful system because it emphasizes quality and not security as the first property, and you get security, you get compliance as these side effects. And so, just a quick aside of some modern defenses, I'm sure you've heard about supply chain security and understanding where things came from, the provenance. AI is a big thing now, and we're starting to talk about the provenance of data, just like we talk about the provenance of your software dependencies. We mentioned earlier software bill of materials, right? That list, the ingredients list or whatever you want to call it, what's inside your image, who created it, how was it created, where did it come from, what steps did it go through to get to me. And then policy as code is also near and dear to my heart. If you have a set of rules that you want to follow, enforce it with code, not with processes, right? That's what policy as code will do. So you could say, well, what is least privilege? Least privilege is a concept, but I can write code to understand what is least privilege. Nothing in my environment needs capsysadmin, right? Capsysadmin is essentially running as root on a server, right? So you can codify, well, at least nobody has that, and you can kind of chip away at these like prior assumptions or bad practices that are in an environment with software. You can run things in pipelines, et cetera, et cetera. And so if we think about these distributed systems that are immutable, we're making new ones all the time, they scale up and scale down on their own, you're not going to be able to manage that and do real cloud security without automating like everything, right? And so that's a lot of the kind of, my focus is like automating meetings, like literally automating everything that we can to support these cloud native environments, right? That have DIE as an attribute. I got a question when I said, are there any things that you would like us to talk about? From Justin. He said, are there security benefits from using an immutable Linux distro over a standard Fedora Debian distro when it comes to running containers? And we kind of talked about this already. I think there are definitely benefits because we should not consider the container a security boundary. If we expect that they're going to escape from the container or that it's not a strong security boundary, having immutability on your system is DIE. It's a good property to have. There's definitely pros and cons to this, but there are certain immutable Linux distributions that work kind of like containers, so that you can patch and unpatch and version like kind of buckets of code dependencies and things like that. Yeah.
I was gonna ask you about this topic too, but
Yeah.
So
like super
one
hot.
of the things that I'm interested in particular is purpose-built immutable Linux distros.
Yeah.
There are a few that are made specifically for running container workloads,
Mhm.
Talos, ISSA, or whatever, right? And the idea behind these is again, it comes back to like patterns, right? Like, those operating systems only have the tools on them that they need in order to run caves.
Yeah.
So from like a stigging perspective, or that kind of stuff, it makes it makes that a lot simpler because you're checking a lot of boxes.
Right.
Like in the stig, like
Yep.
oh yeah, there is no SSH, right? So like, do you have a lot of experience with them at all? Have you made use of like Talos or Kairos or anything?
I haven't used Talos or Kairos specifically. I've used CoreOS
Okay.
and AWS Bottle Rocket are the two that I've used.
Right. So is CoreOS still active?
No.
Though? Yeah.
No, it's not really a
That
thing
one
anymore.
died, right?
That's like 6 years ago experience.
Bottle
Yeah.
Rocket still active?
Yeah, it's still
Okay.
active. Yeah. It's an AWS project that's donated and has a community, and it's pretty much an AWS project. I've stigged a Bottle Rocket before, actually, and it was great. It was a great experience. And you don't ever say that about stigging anything.
No, you don't.
If I recall properly, the only thing I needed to actually do was add firewall rules on it, and it was done. So for everyone else, there are these operating systems that are super minimal for just running containers. And if you think of the microkernel example I gave earlier, where you compile a kernel just for that one application, you make it much more minimal. It's kind of that idea, but they're generalizing a bit to containers, general container workloads. And so, yeah, Bottle Rocket is the one that I've used the most. And in that case, like, there's no shell on it. So, like, you talk about like SSHing into production, like, you can't. In Bottle Rocket, the way you do that is you deploy a container onto that box that has SSH, and it's a bad idea. And they don't like you doing this, but you can deploy these like admin containers or SSH containers, and that's how you get on the box, because the box otherwise does not even have that capability. It doesn't have this like remote connection ability. And so it doesn't also have things like firewalls by default. You have to go kind of like add those. But it is beautiful because instead of a list of 1,000 things to do to stig it, like I think there was 8, and 7 of them were secure by default, and 1 I had to do. Like it was great. In that same project, I had to stig Ubuntu 2204 or 2404, and there was like 150 things I had to do, right? Like it was like, okay, like a week and a half of work, an afternoon. It was great. If your workloads can work in that environment. What I haven't done with these more limited operating systems are like AI workloads, inference, GPU-based workloads. I'm not sure if they have all of that, or if they have like an extension or pluggable approach to add those sorts of features, or how well that works. I don't know. But for standard workload like CPU and RAM, they've worked great in my experience.
Cool. Thank you.
Yeah.
So I've been running into just different issues with portability between different platforms. Say something that, say, a vendor builds for Docker, but I have to run it in OpenShift or something like that. So now
Yeah.
the image from the base image has to change to something like Podman.
Yep.
And I've run into all kinds of small glitchy issues.
Mhm.
Like Red Hat running a cron job a second after midnight instead of a second before midnight. That sort of thing, say midnight. Are there security issues that you're aware of that come up from that platform shift when you move from platform to platform?
So I think the way I would summarize that question is, are there security issues from vendors providing images meant to run with one runtime, but then you running them with another one? And I mean, there are examples of that. The Cryo project had a big issue a number of years ago for similar reasons. They have tried to simplify that with the containerd and runc interfaces. And as far as I know, most projects conform to that spec, but they don't have to. If they didn't, that would be concerning to me. I don't know a lot of projects that don't. I definitely am familiar with the issue you're talking about Podman and Docker, where Red Hat says you can just alias Docker equals Podman and it should work, and that's not true at all. They also don't support like BuildKit. They don't support like the newer ways of building images either, which is like it's not true.
It also sounds like an OpenShift specific problem, which is not uncommon either, because there's a bunch of Red Hat goodness that they put.
Yeah.
Goodness.
Yeah, the kind of distribution problem, right, where your runtime is an OpenShift or even an EKS or AKS or GKE, where it's Kubernetes plus. So, like Kubernetes, to be a certified Kubernetes distribution, you need to be conformant with their conformance tests. They have a set of a few hundred automated tests that you need to run, and you need to be conformant with that. That means that when I deploy a pod with this definition, it's going to deploy a container on the system with this definition. But Kubernetes is such a Swiss Army knife that doesn't actually mean that much. It just generally means that if I want to say if I want to build my business in a way that's easy for me to run in places where we don't have cloud data centers, but we require data locality, like I'm familiar with Canada, a couple provinces require that you run in their province, but there are no data centers there other than colos, like Azure, AWS don't have data centers there. And so for those reasons, people will say, oh, well, if we run on Kubernetes, it's just kubectl apply away and we're done. But in reality, not so much, especially because like some of the magic sauce that they add in is IAM based and permissions based and things like that. That said, I can't give you a long list of problems that I'm familiar with. It's kind of the edge cases and the corner cases that happen, but I'm not familiar with a systemic problem with that where I would caution against it. I would just say that, yeah, anytime that you've got that misalignment, you're going to have the little gotchas.
Thank you.
Not super helpful, I know, but good questions. Any other questions? Don't forget about the giveaway. Yeah.
Okay, so help me out with immutable.
Okay.
So the kernel, the operating system still has vulnerabilities. How do you deal with those in an immutable Linux?
So in that scenario, so just for the recording, you're saying that you have an operating system, it is mutable, it can be changed, but you want this immutable property, you have immutable images running on it, there are vulnerabilities, how do you fix these sorts of things? And the concept really just steps back one more level, and it says, well, great, in order to patch that system, I don't patch it. I make a new one, and I cut all my workloads over the new thing, and I destroy the old one. So it's just cattle, right? If you're familiar with the saying, cattle, not pets, you don't name and feed and love your servers anymore. You just cut them, you butcher them, right? Yeah, so it's not technically immutable, but it's the immutable process applied to those, yeah. All right, any other questions? All right, I've got a bunch of different demos. All right, when did we start?
508.
508. All right, so I'm just going to do my first little demo thing, and then we'll just YOLO it from there, right? We'll just figure out what do we want to do next. Yeah, question? Is there a bathroom? Yes. If you go through here and go through,
Take the first right.
yeah, okay, first right.
All the way to the back.
It's right there, but you have to go through that to it. Yes.
Okay, cool.
Yes. I think Alex can show you if you need it. All right, so, yep. It does exist. There is one. Okay, so I'm on a Mac. Macs are not great for container examples, so instead I made probably an Ubuntu box. I think it's an Ubuntu box. It says it right there, so it's an Ubuntu box. Thank you. Appreciate that. This is an Ubuntu box. Let me say that authoritatively. Okay, and so you'll see me jump back and forth a little bit. This is just the thing I'm going to copy from because I only have one screen.
Just real quick, did you use Terraform to bring that up?
Yeah.
I thought
Yeah.
I saw it.
Actually, I used Terraform right here, and then to provision it, I used Ansible. Yeah. Actually, it's OpenTofu. So,
Oh, okay.
not Terraform, but essentially Terraform. OpenTofu is a fork of Terraform. So, in shells, we've got this special variable, shlvl. It tells you what level you're in, right? You can get into a bit of an inception. And so I have a bash shell open. It's the first level. Great. If I open another bash shell, you can't tell the difference. But if I echo shell level, I'm now at number 2. So it will increment. This is one handy way to know if you're inside of another kind of level of shells. I see some people nodding. They've been here before. That works great for bash, but sh just copies the environment variables from what it was forked off of, so it won't actually change it. That's a little bit annoying. Let's just exit out of this. Oh, I need to SSH back into my server. All right, so we've got this kind of idea of levels, right? And so You can a little bit think of containers like that. We're going to be jumping into like another level, a constrained, forked version of the shell. Specifically, we're going to look at capabilities to start. So I've pre-installed a couple of utilities. One is getCap, which is not packet captures, it's capabilities. And you can see I'm looking up where ping is. So this is the ping that if I actually ran like ping ABC123. And you can see that on the left, user bin ping is what it found, and it has capnet raw equals EP, effective permissions of capnet raw. So it can do things on the wire. Cap is capability, and capnet raw means that you have pretty much raw, unfettered access to the network side of the kernel. Capsysadmin is similar, like you have highly privileged access. There's a number of these that are very interesting. And that is on the file itself. So let's say if I copy that file to my current directory and I look at the capabilities, those get stripped off, right? So I can't just, because I have read access, copy a file to somewhere else, get those capabilities, modify the binary, and escalate my privileges. It strips those off. The Linux kernel is pretty smart about those sorts of things. Capabilities also apply to processes. So if you pass a number in, you can see PID 0. You can see my current shell essentially does not have any special permissions. But if I do a sudo bash, sudo, I don't know, tomato, and I do a get bcaps of my own shell, you could see I have additional permissions, right? So processes can have additional capabilities, right? These effective and permitted capabilities. My point here is just to show that they apply to files, to, oh, well, everything's a file, but files, to processes, etc. There's also C groups. C groups are the way that you limit the RAM or the block I/O or CPU. There's two different versions of it. When I first put this together, C groups v1 was still the thing. It's no longer the thing, so we're going to skip it because in my Ubuntu box, there aren't C groups v1. We've moved to v2. Great. It's a little bit less aesthetic for a demo, but it still works. And you can see that the way that these, the way that C groups look is that they use the proc file system, right? The special pseudo file system. And it's a file that gives you information. And so you can see that again, for my own shell, we are in this scope. So we've got a user slice. This is all users. Then we've got my user, which is user 1000. And then we've got this one session, which is the 50, for whatever reason, it's the 57th session for user 1000 on this system. And we can navigate through the proc file system and see all kinds of things about limiting myself. So you see this big old cat command. I'm really just looking at the memory.max. So I want to see for my session what limits, what capabilities have been imposed on me to restrict memory. And we have the special max. That means that I've got all of it available to me. If I wanted to limit this, I change that, and I can constrain the amount of memory that this process, that my user session is allowed to have. I don't remember why I showed this command, but I think it has something to do with the fact that services also get capabilities. There are these special system slices. That's what I wanted to show. There are these special system slices, which are things other than the user slices, right? And so here we've got the Docker socket, if I run Docker sock, and the Docker service, and we can constrain those. You know, I don't know that anyone, yeah, we can see that it has the service, the Docker service has access to all of the memory. It might not allocate all of that, it might not use it, right? So that's C groups, right? Very, very brief, quick example. Let's combine, well, not really combine. Let's talk about namespaces, which namespaces are a little bit maybe more intuitive to constrain parts of Linux. And we're going to use that to make a container. We're going to use a command called unshare, And unshare is just for running new processes and has a lot of handy arguments for interacting with the Linux kernel, creating different namespaces. Oops. I'll do this. And you can see if I am the Ubuntu user and I run a list of all the namespaces, I get this. And I do a sudo bash, and then I do the same exact command. It's different, right? If I have more permissions, I see more things. Should be very intuitive to pretty much everybody. And I also have the ability to run bash with the special Unix time-sharing unique namespace. So I've made a new UTS namespace with that command, and it's a new bash. Again, the shell level is telling us that I am kind of in as this second level. And let's look at the host name. My host name is IP 10.01.175. Let's change my host name to something new. And I can see that my host name is now new, right? I've just changed, according to this process, I just changed the server's host name. Interesting. But I didn't actually, right? What I did was I changed the host name for that UTS namespace. So if I exit out of that, I'm back up to level 1, and I do host name, I didn't actually change it, right? So this is ways that you can effectively, I don't want to say trick, but you're constraining these processes to think that they, different things, right? They can have whatever namespace you want. So if you've ever went into a Docker container, you probably see like a hash. It thinks that its host name is a hash. It's because it has a special namespace, a UTS namespace. There are also PID namespaces. So these are a little interesting, right? So I'm going to try to do this. We're going to see that I am in this new level, but I really can't do anything. ls cat file, like I can't allocate memory. Like I'm kind of neutered. So I've made a new process namespace. Sometimes you can make it so your process can't be effective. Like it can't actually do anything because you put it in a different namespace and you've essentially broken it. So it's not just putting like 1 or 2 namespaces. It's like curating special configurations of constraints. And it doesn't always work exactly the same way. So if I do that exact same command, but instead of bash, I do shell, and I do an ls, it works once. Then it breaks, right? But if I do it the right way, I can run a bunch of commands because I have set it up to fork properly, right? And you can also see that if I echo the PID that I'm in, the process ID, it thinks it's process 1. It thinks it's process 1 because I made a new PID namespace. So it doesn't know about anything else. So for $20 of Amazon dollars, what do you think will happen if I run PS? An error? No processes?
They get one process, the PS process.
One process? See yourself? How about all the processes? Whoops. That's because PS uses the proc file system and it still has access to the proc file system. Not intuitive, right? Wait, what? All right. So that's all great. We're getting kind of to the end of our time here. So let's just make an actual container. And all of this is online, so you could like poke at this later if you want. So I am root. I think we can do this as root. So I can't, if I run root some empty directory and do ls, it doesn't work. That's what I'm showing here. Like it like purposefully doesn't work because that file doesn't exist. And I'm in level 1. Let's make a directory which is called Alpine. So Alpine is a super minimal distribution of Linux. Got really popular because of containers. And I'm going to download their entire file system. It's small, so I can do that. It took, I don't know, it's 28 meg. It took no time. So let's untar it, whatever. So I've got this Alpine directory, and if I ls Alpine, it's going to look like lsing the root of a server, right? It looks exactly like lsing the root of a server, but I'm not at the root of a server. I'm in my home directory. Okay. So if I ls/bin/ash, in Ubuntu, that doesn't exist. /bin/ash doesn't exist. So nothing up my sleeves, right? I'm not even wearing sleeves. Got too warm in here. If I do a chroot alpine bin ash that says in the alpine directory run bin ash. So now it thinks I'm in the root directory. If I do an ls, I've got this. I've jailed myself, right, into that directory. I can also run an all-in-one command. So this just ran the command and then immediately exited, right? You can see I'm not in another shell. Again, you can see why shlvl is helpful. And you can combine multiple namespaces together. So all of the stuff we just talked about, UTS, the Unix time sharing, that's the host name, a PID namespace, fork so that the ash can actually make multiple processes, and then we're going to chroot into the Alpine directory, and we're going to run bin ash. Ta-da! I just made a container, right? That's it. I ran this ash with a bunch of namespaces, right? In a chroot jail. So if I echo $, I'm PID1. I'm the only thing that exists on this server. My host name is what I pulled from above. If I do a PS, I got nothing, right? We might need the proc file system though, so you really shouldn't end here. We should mount the proc file system so we can PS at least inside of our container. So before, when I ran this PS, it was actually broken. Like, it should have showed PID1 and PID6, the PS itself, right? But it didn't because I broke it with containers. This is the stuff that Docker is just doing for us and making it easy, right? But there's a lot more to it than this. There's a lot more to it than this, but this is a simple example. I don't remember what my goal here was. Hold on one second. Let's just do this. So I just wanted to show again, in that prior container, we can change the host name, and if we exit out of it and do host name, it didn't actually change, right? So that works as well, right? You can just combine all of these things together. And I'm going to skip all of the file system mount stuff. All right. So that's my demo. That's how you can make a container from scratch. Literally, it's like put some files on a file system, run a couple commands, put it in different namespaces. You've made a container. A very naive, simple container, but you can make a container yourself. You can see why Docker or other systems could make mistakes, and we could have vulnerabilities and problems with the runtime. Like, that definitely happens. If people want to get deeper into this stuff, I have 2 labs online where I literally extract the file system from an image, and you can look at like the files that are inside of Alpine on the internet, and you can see other maybe surprising things. Like in the manifest, the metadata of an image, it tells you the commands that were used to build it. So if you passed in an argument, which is the super secret password to get to our internal code repository, that's in the image. Even though you didn't put it in the Docker file, if you passed it in at build time, it's in the manifest of the image. So if you then put that thing on the internet, your internal password is exposed. This has happened to a bunch of different companies, and it's a little bit tricky to catch. You can even see the commands that are used to build it. So I can see that literally this bin.sh, group add, 53150, not root, whatever, like that was used to build this image in this example. All of the history is a giant list. All of the environment variables are a list. All that stuff is essentially public. So you should expect, generally, there are ways to work around this with multi-stage builds and things like that, but you should expect that if you run commands to make an image, those commands are in the image. And so if you distribute that image somewhere, anyone who can access to read that gets that access. So there's, like I said, there's lots of different ways to get secrets in at build time that you can do safely. But if you do it the simple way of --build-arg, that's not safe. Yeah, and I verified all these labs work. We could go through them, but I don't think anyone wants to go through them right now. It's 8:15, 8:10 at night. Just to give you an idea of what is out there, if you want to look at how you can build it to be secure by default, but then run it insecurely, that's in the labs as well. How to cryptographically sign your images to not only say that it's immutable and hasn't been changed, but who did it come from. To generate an SBOM for it. What else do I do? Oh, there's a container breakout too. If you're into container breakouts, we do one at the end down here, ready, set, break. So that's at the end of the 201 lab. And in order to do this, all you need is an Ubuntu VM, and then you run this one command. It sets up all the stuff that you need, and then you can just follow the instructions down. So, cool. Any other questions?
So,
Yeah.
Talked a lot about like breakouts as like a security thing and stuff like that, security concern. So one of the things, are you aware of like Platform One and like Iron Bank and stuff like that,
Yep.
right? So like one of the concerns is, anyone can publish an image to things like Docker Hub and stuff like that. And so if you're thinking about like software supply chain security, like the registry is a problem, right? Because who knows? Even if you're throwing in like your cryptographic signatures and stuff like that. So, do you guys? Is there like? I guess the question is like, what are your thoughts on like registry security and like providing like secure base images and stuff like that? What Iron Bank does.
So, what are my thoughts on registry security and supply chain security and things like that? So, I would start by pointing to Salsa. So Salsa is a project that helps to describe the kill chain, like all the different ways that things can go wrong, from producing, writing software at source code, building it, including into containers, distributing it to people consuming it, dependencies, all of that stuff, right? It's supply chain security. It applies to exactly what we're talking about. And so each one of these little red exclamation points, they talk about somewhere, I forget exactly where, they have a really nice graphic, I can't quickly pull it up, that talks about each attack in each area. So yes, there's things to worry about in each one. One very common problem is the ability to mutate tags on a registry. So if you're not familiar, if I docker pull nginx, what I just did is actually used the default tag latest. So that's the exact same thing as this, right? This part is what's called a tag. That tag is mutable, which means that it can point to different things. That is like the opposite of everything we just talked about with distributed immutable ephemeral, right? So that's bad. Lots of people will just run nginx without realizing that it's this latest tag which can change. If I run it today and I run it tomorrow, it could be different. Also, I don't know how they do their versioning, but something like, let's say 1.2, this is also commonly a mutable tag. But what I could do is I could run that, right? Or something very similar to that. I think I grabbed the wrong hash. But I could run something like that, and I actually pin to that hash. So on the consumer side of this, right, if I'm over here, if I'm going to consume something from the internet, I want to pin it to hashes, and that has pros and cons. The con of it is they ship updates, I don't automatically get them. So if you point to latest, you always get the updates. That's good. But then you always get the updates. That's bad, right?
That's not entirely true, right? You get the updates when you do
You have to do a pull. Well, no. So the point was that if they ship an update and I do a Docker run, it will not change which version it ran. It would actually run the old version. You can, in Docker Compose, have a configuration of like pull always. Kubernetes, you can specify configs to always pull. But that aside, yeah, if it has a version of it that matches, it'll just use that. So same thing with 1.2. If you're running version 1.2 and it's actually 1.2.2, and there was a big vulnerability and they patched and did 1.2.3, and you don't change anything, you're going to keep running 1.2.2. You're not going to get auto-upgraded to the new thing without explicit Docker pulling 1.2, and then you would get the latest hash of that. Yeah, exactly.
The other benefit from that though is like pinning to a SHA tag, right?
Mhm.
You were talking about auto scaling with the distributed systems earlier, right? So let's say you deploy like an app to a K8s cluster, and you don't use a SHA tag, you use a mutable tag, right? And you auto scale, so you get so you deploy an app.
Yeah,
you've
you
got
can
a
be
set of
inconsistent.
nodes.
Yep.
Yeah. Okay. Yeah.
Yep.
Depends on what's in the image.
Yeah, it depends on the timing of when you pull it.
Right.
And you can fill the local registries with images that you've pre-selected to make that better. You can also you can force it to use your controlled registries and only put approved versions in your controlled registries, and you can remove versions that are insecure. So 1.2, the old 1.2 you could remove, and the new one you put in there, whatever, and manage it yourself. And if you force it to, like with a validating emission policy or validating emission controller, you can force it to use your registry all the time at the cluster level. So yeah, there's a lot to.
Suggestion of yours, like that is how you should do it. Is you should manage like your own like registry and then like control it that way.
It is not always my suggestion, but it's a good, easy way to start. And I see lots of people, they have a CI/CD pipeline and they make a Docker file and they just say from foo on the internet, and that's the whole Docker file. They just download it and they push it into their registry, and then it gets grossly out of date and it has all kinds of issues and maintenance issues, whatever. My preference is to not care as much about where you pull it from, to hash pin everything, to automatically update all of your hashes via automated pull request. So have some job that finds that there's a new hash, do a substitution, see if the Git directory is dirty. If so, open a pull request, at which point your test should run and tell you if your stuff is broken. And if it doesn't, you need better tests.
Is that something like Flux or Argo for doing that?
Yeah, Argo or Flux could help with that. There's another one called, oh man, I always forget what it's called. There's another, it's not a CNCF project that does a really good job. Oh, I'm thinking Refactory. It's not Refactory. But it's, yeah, like similar to those things for automatically updating it. I've built like a million different versions of this in like Bitbucket pipelines and GitHub Actions and whatever. It's essentially Dependabot, right? It's just Dependabot, right? So you automatically update the pinned hash, and then you check the provenance, you check the signature. So if you go to I think the 101 lab at the end, yeah. So the last thing we do is so you mentioned Iron Bank. Similar to, so Iron Bank is like a DoD-funded project for storing pre-vet images that have good security processes and characteristics.
That's the idea.
Yeah, that's the idea, exactly, that's the idea. So ChainGuard is a vendor in this space that does a very good job of this as well, and so I pulled down the ChainGuard cosign image, and I just looked at all of the things that they have attached to it, and these are all essentially like security properties. It's got a signature, it's got an SBOM, and it's got what we call attestation. So an attestation is anything you want to say about a thing. So an attestation could be that I vulnerability scanned this and I thought it was okay. We had a pen test and they pen tested this code and they didn't find any findings. Or we pen tested it and they found 1 million findings. Those are all types of attestations. It's a signature with metadata. And so I like transparency and lots of this bits of information and validate that on the consuming side when you pull them down, when you use them and deploy them in your clusters. And if you do a really good job of this, there's very little problems can actually come from a registry compromise. Or like somebody, like what could happen, the worst thing that could happen if you follow that approach is a backdoor gets inserted into some upstream project and it makes it into your project because you've auto-updated to it. That could absolutely happen. It doesn't solve every problem, but it does solve a lot of problems. I'm a huge fan of attestations. I will talk to you for like an hour about just attestations. But I think that the future of things like pen testing and even B2B relationships are attestation based. I can cryptographically sign. Heck, it could be a PDF pen test report. Like, who cares? But like, make these things automatically discoverable, accessible, transferable across companies, so we can exchange information and say, I trust you, I don't trust you, I kind of trust you. There's a project called Alpha Omega that's from Microsoft and Amazon, and it's in the OpenSSF, which is like the CNCF. Anyways, they are full-time, just doing white box code review of popular open source projects, and then they create attestations and they shove them out on the internet, and they say, at this timestamp, we had really smart people look at this thing, and we found this stuff. And they're just spewing that sort of stuff out there, which is insanely useful for really popular projects like your Nginx's and things like that. And I think the more that we can share these, like, I don't know about you guys, but like I see lots of companies that buy pen tests, and they just don't share that stuff. They keep it to themselves. I want to see more sharing of the parts of that we can share, right? Not just blind openness, but more sharing of that information, and make more of like a ecosystem of what do we all think as a community, is this safe or not? Kind of the opposite of how PKI works, where you have like a trusted entity and you just trust what they say. Moxie Marlinspike had an idea for this back like 2 decades ago to replace TLS. I think the same thing can work for software supply chain and security. It's just like we just need to share more information, and we can say, for a long time this has been really good, but recently a couple people are flagging this as sketchy. Or I can just say, anything that Microsoft looks at, I'm good with. And if Microsoft doesn't have an attestation for it, then I need at least 5 other companies saying that it's okay for me to accept this. It's policy as code. You can just make it whatever you want, right? But we need the information to start being shared more so that we can write this policy as code and just really share information. Right? I have a lot more that I could say to answer your question, and we could talk about it after, but I think we're at time. Yeah. Any other questions? Awesome.
I have a small question.
Yeah.
What was the difference when Docker changed from Linux cookie containers and were starting to do their own stuff? Because in the beginning, Dockers were using Linux containers under the hood, and 8 years ago, we just switched to their own build in Dockers. So Dockers are, when you're running Docker, you're not running a Linux container. You're running something else.
I'm not sure exactly what you're referring to. There's been a number of different changes where Docker was the first person to solve a problem, and so they had a unique spin on it. And then there was a standard that was created, and in some cases they then moved to adopt the standard, and in some cases they didn't. Like their image is actually not an OCI image. OCI is like the specification. It's not actually compliant with that. They have a Docker specification for images, but you can translate between them and things like that. They were the ones that created containerd and runc, and they open sourced and spun those out, and people have adopted those, and they still use those in most cases. But things get really dirty depending on specifically what you're talking about. And if we're talking about Windows containers, I don't even want to talk about that. It's like a whole other thing.
I was going to ask.
We don't talk about that. Yeah.
Jails on FreeBSD.
Yeah.
How much different basically jails?
So I'm not a huge FreeBSD person, so I don't have a lot of personal experience with this. Conceptually, I understand that they're very similar. I was not using jails because I was in elementary school.
Jails because they started doing jails and containerization on FreeBSD before.
Yeah, that's a lot of the origin of this. And they ended up taking a lot of inspiration, and things got ported into the kernel and then became more useful broadly. Yeah, exactly. And that's, the whole inspiration for namespaces and C groups and things like that. And then we started getting LSMs, the Linux security modules, which are separate, the SE Linuxes and AppArmor, yeah, exactly, etc. All right, I'm going to call it. If you want to hang out, I'm going to hang out. We can keep talking about this, but thanks everyone for coming out. Also, if you want to see about Container Escape, this is my favorite article on it. It's also linked in these
Are you sending
labs.
the links out?
It's up to you.
So johnziola.com is one of them, right?
Yeah.
We will also put on the member or on the ISSA page links to John's site and the presentation
And we
in
will
the
upload
calendar
the video
meetings.
to the Hackers Guild website as well.
Yeah, and we'll upload the video to Hacker Guild and things like that. Yep. And all of my presentations are on GitHub under Monoprezo, John Ziola. So if you know how to read HTML and Markdown and stuff like that, you can figure it out.